We will see module 3. So these are the different topics in the module 3. We will see each topic. Continuous channels and continuous sources. So in the module 1, module 2 as well as module 4, 5, 6, we are dealing with discrete sources or discrete channels. But in the module 3, we want to see the continuous channels and continuous sources. Okay, it's entropy, bandwidth requirement, like that some topics. So here this is just a schematic representation of a continuous channel and continuous source. There is a channel, the input is x of t. X of t is the representation of continuous time signal. It is given to a adder. That is, this schematic representation shows that always there is a presence of noise in the channel. So in the channel there will be addition of the noise. So that noise is band limited white Gaussian noise. It is represented as n of t. So n of t plus x of t will be z of t. Okay. So when the input signal is passing through a channel, it will be get added with the noise and the resultant will be z of t, and that is given to the modulator. So now we will see the differential entropy or continuous entropy. So this is very much similar term of the entropy which we have seen in the discrete sources. Okay. So what is the entropy expression there? H of s, that is the representation, it is equal to sigma p of x log base to 1 by p of x. So here h of x, that is the representation, x is the continuous signal. Then instead of sigma, here it will be integral. Instead of p of x, here it will be f of x. That is probability density function. Since it is a continuous time signal, instead of probability, we are using probability density function. It is represented by f of x. Probability density function you have already studied. Okay. So integral f of x log 1 by f of x dx bits per sample. Okay. So next is the mutual information of continuous noise channel. So I of x comma y is the representation of the mutual informations. You can see the three expressions here. All these three expressions we have studied in the discrete sources. Okay. So now we will see h of x comma y expression. It is the joint entropy. So here you can see double integral. Okay, there it was double sigma, but here it is double integral. F of x comma y. Okay, log f of x comma y dx dy. So if you are comparing this expression with the discrete source expression, then you will get how to write that. Okay, instead of p of xj comma yk, here it is f of x comma y. That is, instead of probability, here it will be probability density function. That is only the difference. All other concept, that is same for the discrete and continuous. Okay, then this is the conditional entropy, h of x given y. Double integral f of x comma y log f of x given y dx dy. So f of x comma y is the joint probability density function, and f of x given y is the conditional PDF of x given that y equal to y. Okay, that is there it was h of x given y is equal to double integral p of xj comma yk log p of xj given yk. Okay, so here only one change, or I can say two changes, that is the probability, that is probability density function, and double integral, that will become double sigma, that will become double integral here. So now we will see the properties of mi. The first property is I of x comma y equal to I of y comma x. Okay, so here I of x comma y, this is the expression double integral f of x comma y log f of x given y f of x dx dy. Okay, again I am repeating, this is that this expression is very much similar to the discrete source. You just compare that expression and this one. Okay, then I of y comma x, actually here it is written I of x comma y, but here it is actually I of y comma x. That is equal to double integral f of x comma y log f of y given x divided by f of y. Okay, so now based on the base rule, we can write f of x given y by f of x equal to f of y given x divided by f of y. Okay, that is f of x given y into f of y equal to f of y given x into f of x. That is base rule. So based on that base rule, we can say that these two expressions are same because these ratios are same. So I of x comma y equal to I of y comma x. That is the property 1. That is similar way we have proved the first property for the discrete sources also. Okay, only thing you have to do is that just compare that expressions, that's all. Then the next property is it is a non-negative value, mutual information, I of x comma y greater than or equal to 0. So I considered I of x comma y the basic expression, that is double integral f of x comma y log f of x given y divided by f of x. Okay. So for that f of x given y, I substituted this because based on the base rule I know f of x comma y equal to f of x given y into f of y. So f of x given y can be written as f of x comma y divided by f of y. Okay. So when I am substituting f of x given y as f of x comma y by f of y, I will get this. Okay. Then I am taking ln2 outside, 1 by ln2 outside. Then I will get like this. Then when I am applying the inequality ln 1 by x is greater than or equal to 1 minus x. I am considering that inequality. Here I am taking x equal to f of x f of y divided by f of x comma y. Okay, that is the x. I am considering x as like that. Then ln f x comma y divided by f of x f of y, which means this term. Okay, what will be this term in terms of x? It is ln 1 by x. X എന്ന് പറയുന്ന f of x f of y divided by f of x comma y. Then ln 1 by x ആണ് this term. So this is greater than or equal to 1 minus x. Okay, I can write like this. Then multiply both side with f of x comma y and double integrate. Okay, so double integral f of x comma y, then this term as such, greater than or equal to double integral f of x comma y, then this term. Okay, so now we will see the LHS. Also one more operation we are doing, dividing both side by ln2. Then 1 by ln2, here 1 by ln2. Okay, then LHS, that will be the expression of this, that is I of x comma y. So here LHS I of x comma y, that is greater than or equal to 1 by ln2. Listen this part. So here when I am multiplying f of x comma y inside this bracket, and the double integral f of x comma y minus f of x f of y. Okay, so I can write like this, integral minus infinity to plus infinity f of x dx, integral minus infinity to plus infinity f of y dy. So this is the probability density function, isn't it? F of x comma y, also f of x, f of y, all these are probability density function. So we have studied in maths as well as in analog communication, the area under the PDF curve, that is probability density function, that will be always 1 if it is integrating from minus infinity to plus infinity. So here we can substitute this double integral with 1, this integral with 1, this integral with 1, which means RHS I will get as 0. So I of x comma y greater than or equal to 0. That is the second proof. Okay. So now we will see the third property, I of x comma y equal to h of x minus h of x given y. So h of x given y I am writing like this, already we have seen this expression. Then h of x equal to, this will be the expression. Then we know integral minus infinity to plus infinity f of y given x dy equal to 1. So this derivation procedure is similar to the derivation which we have done for the discrete sources. There also we have multiplied with 1, a term with value which is equivalent to 1. Okay, so there we multiplied I think p of yk given xj. So here f of y given x dy equal to 1. So I am multiplying this term with this h of x. Okay, then I am combining these two terms, then I will get f of x comma y, because f of x into f of y given x is f of x comma y log 1 by f of x dx. So that will be h of x. So h of x given y is here, h of is also here. So why I multiplied this term with h of x? Because I want to get h of x in terms of f of x comma y. Okay, so that is why I multiplied this term. And here h of x minus h of x given y, I am doing this operation, then I will get log x given by f of x dx, that is I of x comma y I will get. So this is a very simple operation. Okay, I am just writing the expression for h of x given y, I am writing the expression for h of x, but that h of x I am converting in terms of f of x comma y by multiplying this term. Okay, this will be 1 because it is a PDF curve, so it is the area under that curve will be always 1. Then just subtract it, you will get the expression for h of x given, no sorry, I of x comma y, I of x comma y. Okay, so now the next property is I of x comma y equal to h of y minus h of y given x. Okay, so that is the property 4. So in that property 4 we know that I of x comma y equal to h of x minus h of x given y. I am explaining about the last line, okay, in this slide. So I of x comma y equal to h of x minus h of x given y, that is already we proved. So now interchange x and y. So I of x comma y will become I of y comma x, h of x will become h of y, h of x given y will become h of y given x. Okay, and we know that based on the symmetry property I of x comma y equal to I of y comma x. Okay, then we can say that I of x comma y is equal to h of y minus h of y given x. So these are the 4 properties of the mutual information. Okay.